So
let me introduce the next speaker, and this is mross, I guess. He is master in Bonn and in Göteborg. Now he's working at the MIT with Santiago Rodriguez, and he will talk about the control expansion for certain non-fermitic metals.
All right, well, thank you. Thanks for the nice conference. I had a pretty great week. And today I want to present some work which I did with John, Wong, and Central at MIT. And it's about a controlled expansion for certain non-liquid metals. So this is what I'm going to talk about. Firstly, I want to tell you what I mean by certain non-liquid metals. And then I'm going to present the earlier uncontrolled approaches to this very material. Then, based on its shortcomings, I will then develop our controlled expansion, which, as I will claim, cures these shortcomings. And then, since it's sort of technical, I will briefly discuss the physical intuition, how one can understand what the state's actually like, before wrapping up with some final remarks. Well, we all want to know what a non-fermi liquid is. So generally, in quantum physics, most of what we're trying to do is solving this kind of Hamiltonian, some electrons with interaction, which we can't do, which is good, because that way we all have a drop. But nonetheless, even though we can actually solve this, there's quite a lot we understand about this type of Hamiltonian. Namely, Landau pointed out that in many cases, the solution to such kind of Hamiltonian is in fact not that different to the free electrons. Namely, the electrons basically retain their identity. They still have spin, they still have charge. They are well-defined quasi-particles which form a Fermi surface. There may be some slight changes, like an affected mass or velocity, but overall it's still fairly similar to the free electron. And one can just describe this in a hydrodynamic description, meaning that instead of using these inconvenient Fermi operators, one can describe most of its properties simply in terms of bosonic densities. From a modern point of view, one would say that the Fermi liquid state is stable against most interactions in an RG sense. There is the idea of universality, which extends beyond the thermodynamics and the long wavelength properties which are already present in Landau's Fermi liquid theory. Namely, there are also certain short distance properties like the 2KF singularities and the BCS instability, which are also universal for Fermi liquid and don't really depend very much on the specific details of the system. Another modern concept would be emergent symmetry. So the Fermi liquid state has at low energies a large symmetry, namely U1 for each point of the Fermi surface. So the number of fermions of each point of the Fermi surface is independently conserved. So basically the symmetry of the state would be U1 to the power infinity.
But that's a very eloquent way to say that this state has the same symmetry as a band structure.
Sure.
Yeah. Thanks.
So, but now what we're interested in is non-Fermi liquid metals, which is not quite as well defined as a Fermi liquid. Mainly the only thing we're saying as well is not a Fermi liquid. And in particular, we're interested in metals which are not Fermi liquids. And we take the point of view that what defines a metal is basically that we have something like a Fermi surface, which is a finite density of gaseous modes. And such non-Fermi liquid behavior is seen quite frequently. I mean, many examples are, say, in 1D system, Buttender liquid, in quantum Hall systems, or in the cuprates. And generally, it occurs in the presence of a nearby critical point, or when interactions are very strong, hard to control. And even though we understand some particular systems, or maybe some aspect of some of these systems, one cannot apply the usual methods which we like to use in atmospheric physics. And there are only very scattered proposals on how to treat particular systems. But there is no overall framework how to even classify these kind of systems, much less describe their physics in any precise way.
So usual Fermi surface, it doesn't have finite density?
Sorry?
To zero? What does the density of gapless modes does for Fermi liquids?
What do you want to do? What does it?
So
What's the denominator in the density?
Yeah. You're saying that critical Fermi surfaces have finite density of gapless modes. What
Right.
about just free Fermi surface, free Fermi gas? What does it have?
I think it has high density of gaseous modes.
Oh, but you're saying this is special critical Fermi surface.
Oh, no. I'm saying that I want to call a non-Fermi liquid metal a something which does not fall into the Fermi-liquid feature. It has different properties other than the universal properties which you know from a Fermi-liquid, but it has still one thing in common, which is this finite density of gaseous modes.
So you haven't explained in what ways it's different. You only said in what ways.
Yeah, I saw it. Yeah.
But does your definition exclude points, like having a finite set of Dirac-like points, or does it include that as well? In other words, do you have to have an extended Fermi surface,
Yes.
which is some sort of a closed pocket,
Yes.
or maybe line that perishes at the end of Brillouin zone or something like that? Yeah, it's an extended line.
It's an extended
It's
line.
not a point.
It's not a point, yeah, exactly.
Okay, thanks.
So more precisely, or more technically maybe, what I want to consider is a certain class of non-Fermi liquids which you obtain by starting out with a Fermi surface and coupling it to some gaseous boson, which in particular one can think of just as an immersion gate field, or say some order parameter of a nearby critical point. So at the critical point, generally, there will be soft fluctuations in the order parameter, so the action of fermions coupled to the order parameter will be of this type of form. For the kind of physical systems we have in mind, one is, of course, the quantum spin liquid, which Sandra talked about. Particularly, this is the phase diagram of the coupled T organic, which is a gaseous mod insulator, at least up to some very low temperature region where it's quite possible that there might be some instability to some different state which might have something to do with spin on parent. But in this state, there does appear to be finite density of these gaseous modes, but this thing does not even conduct charge, so it's very different from the under Fermi liquid, because the quasi-particles which we appear to have no longer carry charge, so lost that quantum number. And similar materials in this one are the DMIT, which does not even have this sort of like transition down here at very low temperatures, but I don't have a nice picture for that one. Second example would be the electronic dematic quantum critical point, which is, again, it's rather frequent, typically in the cuprate or in the pnictides. And the idea is that electronic dematic, what it means is that lattice rotation symmetry is broken, but translation symmetry remains intact. I think we had it in the previous talk earlier today. In terms of the Fermi surface, one can imagine, say I start with a circular Fermi surface, and as I tune some parameter, the Fermi surface will change shape, so it becomes kind of oblong. Now this clearly breaks rotational symmetry, but the Brillouin zone is still the same. Like, there's no change in the translation symmetry in the system. And one order parameter for such a nematic would, for instance, be this. Okay. And so for this particular model, we want to describe the system like only precisely out very close to the critical point. Whereas for in the previous phase diagram, we believe that this kind of a model will describe the model insulator and so the earliest approaches just consist of doing the random phase approximation, which generally is very successful in at least capturing most of the basic physics. So diagrammatically, it just consists of calculating the lowest order bubble diagrams, which is rather straightforward to do, and this found out early on that for the boson one gets this kind of a Landau damping form. But for the fermion, so if you take this this Landau damped boson and calculate the fermion Green function, we find that the lowest order, like the strongest frequency dependence, comes with an exponent which is smaller than 1, let's say here. Which means that the Fermi liquid, which we had previously, is destroyed, and in fact already at the RPA level, we are at a state where the quasi-particle has completely lost its coherence.
Can you remind me that first result omega over k, what limit does it presuppose? I mean, in general, I imagine what enters is the conductivity, omega, mono omega times conductivity, AC, k and omega dependent conductivity. So what is the
the order of limits, you mean?
Yeah, the order of limits.
Like
what?
Omega going to 0 first.
Omega goes to 0 first, okay. That's DC. And this is at 0 temperature, right?
This is all, yeah, everything I'm going to talk about will be at 0 temperature.
No, it's not a DC limit. It's not a conductivity limit. Conductivity limit is k equal to 0.
Oh.
So he keeps k and then makes omega go to 0. It's a damping.
Oh, it's like transfers. It's what you would compute for Meissner effect.
Yeah.
Yeah. Okay, it's that.
It's a Meissner, like analog of Meissner.
Okay, thanks.
But this is in 2 dimensions.
Oh yeah, it's in 2 dimensions.
Let's not forget that.
Yes, it's in 2 dimensions. That's absolutely correct. So, even though RPA is, a priori not that justified, one can still learn something just by looking at what we have obtained, like the green functions on the previous slide. Firstly, that we have this boson fluctuation. So for the boson, the frequency scales as of k to some exponent, which is in this case 3. For the fermion, we have the exponent 3/2. And in general, the fermion green function will be something of this type. Just as the scaling in here, and some exponent, which at RPA level will just be given by the fermion exponent. But in general, one might expect that if one includes higher order corrections, that there will be some anomalous dimension which will make alpha become different from 1 and will give 2 different dimensions of the fermion green function. But the most important observation from this point here is that typically, like for low energies, the boson momentus will be much larger than the fermion momenta. And this has an interesting consequence, namely when we have some fermion sitting on the Fermi surface, and it will scatter with some different fermions sitting here on the Fermi surface, then the only way they can exchange like a large amount of boson and still remain close to the Fermi surface is if these 2 points have the same tangent. So the fermions can scatter from here to here and this way. Because if I had instead had a fermion sitting here and a fermion sitting here, then this guy would scatter far away from the Fermi surface, and that would be less important for the low energy physics. So Buczynski pointed out quite early on that in fact it's sufficient to just consider fermions which have parallel pieces of the Fermi surface. This kind of approach was used by many people subsequently, namely to cut the Fermi surface up into many patches and only consider the interactions between fermions living on opposite patches, or more generally patches with parallel tangents. And then in the end, once one has solved the theory, one makes the consistent to check that, well, if one adds inter-patch interactions, they are in fact irrelevant under RG. So this is then the action modified to describe the just 2 patches. So S would be a parameter which picks out the patch left and right, which in this case would take plus and minus. Eta is just put in for convenience. Principle would be 1, but we'll see it's going to change. And this is written down the interaction as appropriate for the gauge field case, namely that fermion on this side and this side will cover with opposite charge in the gauge field. And this is as before, just the gauge propagator.
So why isn't there a K in front of this second term?
Oh, that's a KF.
Oh, it's at KF.
No, it's basically KF.A, right? But then the
Right.
KF is like a scale, like you can scale out basically all KFs and
Okay,
Fs.
that's fine.
Yeah.
And I guess it's not important. There's also corrections to it that involve derivatives, but does it sub down?
Right.
It doesn't matter because he made it flat. So
Right.
it doesn't matter whether.
No, you don't make it flat. Actually, keeping some curvature here is quite important.
Well, you do it in the kinetic energy term, but not in the coupling. In the coupling, it's
Not
flat.
in a coupling.
In the coupling,
Right.
it's flat.
So coupling looks like density coupling with a sign.
Mm-hmm.
That's right. Yeah, exactly.
And you might also notice that here I snuck in this factor 1 over square root n, which leads on to the next slide, namely, what people tried to do next was generalize the system to n species of fermions, which is quite a popular tool to try and control a theory, and then hope that in the large n limit, the theory does indeed become perturbative, and then that as one extrapolates from this large n limit down to finite n, like n equals 2, which is the most typical case, that most of the physical properties will remain intact. So there's large amount of literature on this particular approach, and the theory is basically believed to be solved for more than a decade. And then recently, Sunzig pointed out that there are in fact some problems with this kind of theory. And that we see best if we consider the scaling which is appropriate with these RPA level green functions. Namely, it's the kind of scaling which we need if we want to keep the direction to marginal. It's easiest to just look at the propagators and then see that we need to scale omega basically as ZB, omega as ky to the ZB. And here the epsilon is just the distance of the fermion from the Fermi surface. So it would be, say, kx plus ky squared. And so the scaling is what? Kx should scale as ky squared, omega will scale as ky to the ZB, and then the appropriate fermion scalings. And this is why I previously introduced this factor eta. It turned out that like all terms in the action are marginal, but the eta actually scales to 0. Which will in principle lead to various kind of divergences in the green function. So if I write down a fermion green function on the Fermi surface, so this term is 0. I don't do
for ZB bigger than 2, right?
ZB is, yes.
It's only for ZB bigger than 2.
Yes, that's correct. I mean, at this point, I'm still at the original model, so ZB should actually still be considered 3 at this point, because I haven't changed it
Or
yet.
3, sorry.
So the original model is like, just compare here, like the exponent for the boson is just k squared. So here, like the same theory, just written out in terms of patches, has ZB equals 3.
I guess I'm pointing out that eta scales to 0 only if ZB is bigger than 2.
Yes, that's correct.
Otherwise,
But in the model which I'm discussing so far, which has ZB equals 3, this is the case, and yeah, exactly. So what happens. So in that case, a fermion on, like if I don't have the RPA term included, a fermion on the green function will, there's a divergence as eta goes to 0. Namely, I get 1 of eta, and if eta flows to 0 under ZRG, will give this kind of divergence. Now if I just replace the free fermion by this RPA propagator, this will cure this divergence. So then I can safely let eta go to 0. But then instead of having this a small factor, like a small factor eta in the denominator, I have a small factor 1 over n. Which again, if I put the fermion on the Fermi surface, will lead to an actual n in the numerator. And this is a basic source of the problem, which Sunzig pointed out, that whenever I have a fermion which I can keep on the Fermi surface, this diagram will in fact get an enhancement factor n. And thus violate the normal counting which you use for large n, namely each vertex is 1 over square root n and each loop gives you a factor of n. This can be made more rigorous, more formalized, and he's found a rather nice way to show that actually at each order of n there's an infinite number of diagrams which will contribute. Which means that the theory is really uncontrolled. I mean, unless you find a clever way to sum up an infinite number of diagrams, you don't really know what's going on.
Can you say again, fermion, that point number 2?
Oh, fermion on the Fermi surface means this guy is 0. Right? So this guy has flown to 0 now. This guy is 0. So the green function is just n over omega to some power. Right? So for each of these green functions, I may in principle get some enhancement factor of n. Now, of course, some of the integrals are going to remove these divergences. So one needs a bit more care. So then you can, well, he derives a very special kind of different diagrammatic representation which allows him to keep track of how many of these fermion propagators are going to give enhancement factors of n.
I was just thinking of it more, I guess maybe technically, you just integrate over the frequencies and you pick up fractional powers of n from doing the integrals. You know, let's say you have a fermion loop. When you integrate over momentum frequencies, then you get fractional powers of n. So then n's are not just coming from the usual number of flavors, but it's coming from just this prefactor number.
Right. I mean, in principle, it's true. Yeah, as I said, like there are factors coming not only from the loops but also from this. But I mean, if you just do the diagrams, you find out that there are never ever any factual powers of n. It just turns out that you get a certain number of integer powers of n in the numerator.
Okay, that's strange.
Right. So anyway, so this was basically the main point that, well, this theory, which has people believe to be solved, and which people have been using to describe, say, this fermion liquid fact some serious problems, and that unless you find a way to sum those diagrams, you're in a bit of trouble. But unfortunately, that's not even the end of the story. Namely, a bit later, Subir and Max pointed out that if you calculate, if you do this large n expansion to 3-loop order, then these kind of diagrams are going to give you a contribution to the Boson propagator, which is in fact leading order over even the bare term. In particular, for the matter case, say, it has a negative sign, and so as n gets large enough, independent of what c is, this term will be negative, which means that one expects that the system is going to order at some moment, meaning that translation symmetry is going to be broken. So not only is the theory uncontrolled for large n, but in fact it appears that the theory is not even stable for large n, which makes the idea of extrapolating, well, kind of suspect. I mean, if we're solving it in a place where the theory is not even stable, then it doesn't seem very likely that if just extrapolating is somehow still going to survive physics. So this is basically the main problem of the large n expansion. And now I want to discuss how that can be circumvented. In fact, there has been a different approach to this kind of problem by Wilczek in the 90s, where they kept n finite and instead induced the second artificial parameter, namely the Boson exponent, and do some, well, perturbative RG epsilon expansion in this parameter, which is technically rather complicated. When the leading order is easy enough, one can just do it and it will agree with RPA, which is not very surprising. But for higher orders, I mean, if you ever tried doing epsilon expansion to like several loop order, like I didn't know how to do that anyways.
But why not do lowest order and epsilon in arbitrary n? Why do you need to combine 1 over n extension n?
No, as I was saying, like this approach is valid for any finite n not being very large, and then perturbative in epsilon.
Right.
Which the problem is that going to higher orders than epsilon is very tricky. At this point, n is not a parameter. N is not an expansion parameter. It's just a number which you put in. So if you want to go to higher orders, this is your parameter. So you need to go to higher orders than epsilon.
Okay.
And that is quite difficult. So what we instead propose is to combine their small epsilon parameter with the large n, which was tried previously, and we find that indeed this precisely cures the problems of the large n expansion from before, and then we can use this theory to calculate various properties basically in the same way as in the normal large n, which is well known and fairly straightforward, even if the integrals may be challenging. But in principle, this is much, much easier to do than some higher order epsilon expansion. So this is the kind of action which I want to use. It's basically, it's exactly the same as written down before, just I write now 1 plus epsilon instead of ZB. So it's exactly the same I had a couple of slides ago. And calculating the Boson propagator, well, it's clearly not going to change, namely because the fermions don't know anything about the epsilon. So if I just calculate, again, some of that in term, it will not change because I just changed this little factor in here. What is going to change, however, if I then use this Boson propagator to calculate the fermion wave function? And then what happens is, instead of getting 1 over n, I get 1 over epsilon n times some prefactor. So as before, when I had the factor of n getting to the numerator, now instead I get a factor of epsilon n to the numerator. And so if I take epsilon to be small, such that epsilon times n is of order 1, then each of these enhancement factors, which were of order n previously, are now order 1. On the other hand, the other factors of n which we get, namely from the vertex, from the number of fermions, they don't care about this epsilon. So they will be as before. Meaning that the original n counting which people had been doing before something came along and point out the problem is now restored. So we have the slight inconvenience of having a different exponent here, but in principle the machinery of the large n has been restored.
And because this is long-range interaction, a non-analytic in K, there are no corrections. There should be no corrections to kinetic energy for A.
I mean, okay, that's
to that
something which we can now verify in the control expansion.
Right.
So for the
In other words, the epsilon does not get corrected.
Yes.
There's no anomalous exponent for that.
That's in some sense the condition why we can do this. And this we can check consistently that up to like the 3-loop diagram this is in fact correct.
Can you repeat that, please?
Sorry,
Just
what?
repeat the whole thing.
From where?
From his question. Just
Oh,
your-
his question was this, if this epsilon, if the exponent for the boson does get changed. Because, you know, in principle one might expect that if I add corrections to my self-energies, that I will acquire anomalous dimension for, you know, both the bosons and the fermions.
Yes.
And if I do acquire dimension, then putting it in here, then I can't really use it as a control extension parameter.
Yes. But you say that doesn't happen.
I'm saying that it does not happen to a certain order in 1 over n. It doesn't happen at all if I do not include fermions of different types of Fermi surface. So if I just consider a single patch, then it can be proven it doesn't happen.
Mm-hmm.
If I do consider both patches, then at least we calculated to the 3-loop order that it doesn't happen. Yeah. So back to the next slide. If we go beyond RPA and take a look at the 3-loop diagrams, then the boson remains unchanged. I mean, it still gets this square root n piece, which Max and Tobias had found, but now this square root n piece is suppressed by n squared. So it's just, just a prefactor of the boson term, which is not going to change its sign. So it doesn't actually change anything. Now for the fermion, at 3-loop order we do find anomalous dimension, namely from these 2 diagrams. So the notation is in this case that the dotted line represents a fermion on one side of the Fermi surface, and the straight, like the full line, is a fermion on the opposite side. And well, these are almost the same diagrams, exactly that here the scattering is in the particle Hubble channel. So here particle and the polar scattering, and here it's in the Cooper channel. So here the particle and the particle scattering. And when we calculate the sum of these 2 diagrams, we can find an expression of this sort. So this is just a function of order 1, which we can evaluate numerically. It's not very difficult, but I mean, we don't have an expression for it, unfortunately. But here we find like this sort of cutoff dependent piece, which will give the Fermi dimension. And then just by exponentiating this, well, this should be like understood as the first term of a bunch of diagrams which will overall sum up to a contribution of this sort. And again, the signs are different for the gauge field and the nematic case. So for the gauge field case, this exponent which we find is actually bigger than the Bayer exponent, which means that the RPA form is not going to be changed. On the other hand, for the nematic case, the new exponent which we find in here is more singular than the Bayer exponent. That means actually in that case, the exponent alpha, which is just 1 minus dimension of the fermion, does acquire a correction. And, well, at least in this controlled expansion, we can calculate this exponent and then extrapolate to n equals 2, x equals 1, which is the idea of this approach. And then we find that, well, the exponent is 0.33. So, well, once we have the green function, this kind of guy, we can just integrate the green function to get the tunneling density of states. And then rather than having just a constant, as in the Fermi liquid, we find some power law suppression directly at a frequency mean 0. That would be like a physical signature of this kind of, some physical signature which shows up at 3-loop order.
For the gauge field, what you recover is basically an RPA type calculation where some epsilon is set to a suitable small value. Isn't that the case? In other words, all the diagrams that otherwise would have created trouble for you in this new approach are dropped, basically.
I mean, I don't know what you mean by diagrams that created trouble for you. I mean, I have all the diagrams which might or might not create trouble in a normal large n expansion. Right? The only diagrams which this double expansion epsilon n drops are the, like, say, diagram which with 10 fermion loops and stuff like that, which in the uncontrolled approach may, depending on the details, actually contribute to first order, second order, and n.
Yes.
So those are the diagrams which with this expansion shows out. But there will still be like non-trivial contributions to the boson propagator, namely this, this diagram we had earlier, this kind.
That's still included.
That's still included. But this now, if I have this guy here gets suppressed by 1 over n squared. Right, so we check that it doesn't diverge, and it's suppressed by 1 over n squared. So then just normalize this coefficient here, so it doesn't do anything drastic.
Sorry, before, I'm trying to understand.
Yeah, you lost me a little bit.
There was a 1 over n squared before, but they got killed. So in this calculation, it's uncontrolled.
Yes.
Right? And so there they had one, should I think of it as they had 1 over n squared, and then it got canceled by n squared, but now your n squared in the numerator got replaced by epsilon n.
Yes, that's correct.
Squared. And so then that's about a 1.
So overall there's still a 1 over n squared, which then...
I see. That's
But then that just sounds like what I said. You see, when you started with your initial, when you motivated your approach,
Yeah.
you said you can do standard 1 over n experience and pick up diagrams,
Right.
and people thought that's enough.
Right.
And then you explained to us that there are dangerous diagrams that arise that interfere with all of these orders, different orders in n,
Right.
and contribute to them. And you now are using epsilon to get rid of those diagrams. Or are you, in fact, filtering some of those diagrams in?
I would say this diagram is still present, but now it's weak enough, it's suppressed enough that it cannot
So
run the
it's,
system in
but
stable.
it just takes its rightful place in a conventional 1 over n
Right.
hierarchy.
Yeah, that's
Okay,
exactly.
okay. So that's what I want to understand.
Yeah.
So you are using epsilon to shoot the dangerous diagrams. In other words, you put them in their place in a conventional 1 over n ordering.
Yes, that's one way to say
That's
it.
right.
Okay.
I mean, like, if he went to lowest order in 1 over
Yeah.
n,
Then he
he
would
would be
get
setting this to 0.
Yes, of course, I understand that.
So
But it
this
would
has
eventually appear in the higher order in conventional 1 over n.
Right.
Yes, that's correct.
So can I ask, so this calculation for the fermionic propagator that corrects the epsilon, corrects alpha if you wish, from 1, that's not been done. That's if you guys are the first ones to do this? Or?
I mean,
Or
it
has
has been
there
done in the uncontrolled limit by Max and Zubir, where they just had ZB equals 3 and they find a different value, but I mean, they don't really know what it means so much.
But they calculate in an uncontrolled way this correction to the fermionic propagator.
Yes.
Momentum dependent correction.
Yes.
I see.
The problem is, in their case, that invalidates the whole thing. Because at large n, this one is bigger. At least for nematic, it's bigger.
For the
than-
fermion it does not, but for the boson it does.
Yeah. But now you say, okay, fine, if epsilon is small, for fixed epsilon times n, this is still down in 1 over n expansion.
Right.
Do you guys have some RG scheme to show that, or you do saddle points basically, or you do, you haven't tried to do an RG scheme where you actually show that the whole thing resums to these power laws?
No.
You haven't done that, okay?
We haven't-
It's,
we haven't had the
I think in
option.
this approach, it's a little bit of a extrapolation to believe that, your epsilon times log epsilon is the beginning of a series of epsilon times power series and log epsilon. Or have you looked at that?
No, we haven't targeted anything beyond the diagram, so no. But yes, we believe it's still reasonable to assume that.
It would be nice to try and do an honest RG calculation.
I mean, what do you mean by an honest RG calculation? You mean calculating the next order diagram and seeing if it actually is the second term in such an expansion?
Well, yes, in the RG, where you're not just calculating some large n saddle points and correction to that saddle point, you're really coarse grain, integrate degrees of freedom out, and observe this thing emerge. Then, very naturally, you find a fixed point, and that fixed point then automatically has all these logs, add up in power series and amounts to correcting the power epsilon sub p to 1 minus some anomalous exponent. So here you don't know this at this stage.
Right. That's correct. No, I mean, in principle, what you're saying amounts to exactly the Maya-Filter approach. I mean, if you want to do the RG, you need to control it somehow.
Right.
And then that you can do if you don't want to do large n, as you don't seem to do. You can use the epsilon control parameter. Then you have to like calculate this epsilon expansion to some higher order, which I claim is very difficult. I mean, this thing is in principle straightforward. You write down the integral and you can kind of solve it with the computer or something. It doesn't involve like any actual thinking, which the epsilon expansion certainly does. Right. So yes, this is basically the most technical part, I think. It's concluded. So I try to convince you that, well, we can control the expansion now, and we find changes in this particular case for the nematic, not for the gauge field case. And for the nematic case also it has this direct consequence which might be measurable in the experiment. Well, if one finds a way to actually tunnel. No, for the nematic case this is balancing because there the particles are actually electrons. So one can just tunnel electrons and might look for such a suppression in the tunneling. Now, let's step back a little bit from the technical stuff and try to understand, based on physical rules, like what's actually going on, what are the governing principles, and can we somehow, just on physical grounds, decide what kind of diagrams are going to be important and how are they going to affect things. And so basically, we have two main features. One is, well, just basically tree level, which is smearing of the lambda quasi-particle, just the RPA destruction of the quasi-particle coherence. Second feature is Ampere's law, namely parallel currents attract, which in our picture means that, well, we get attraction between a particle on one side of the Fermi surface and the hole on the other side, and we get repulsion between particle and particle on the Fermi surface. This is in the gauge field case. In the nematic case, because there's a sign, they just get switched around. So then there will be like anti-parallel currents here and parallel currents in this side. There's a competition between the two effects, and when I write down any vertex, the destruction of the quasi-particle will generally tend to weaken this vertex, whereas the attraction due to Ampere's law between, in this case, a particle and the hole, will try to strengthen the vertex. That's what I just said. And this is, in fact, we find that we can use this reliably to determine the sign of diagrams before we do the calculation. You can use Lenz's law in electrodynamics to fix the sign without keeping track of them very carefully. This actually works for all diagrams which we wanted to check.
So can you explain that again? So I missed it. Let's say the first one.
Oh, and if you imagine you have some vertex which you want to consider. So this vertex will be, once I include the set energies, which is basically then our new tree level scaling, then this will tend to weaken this vertex. That's just because the quasi-particle itself is losing its identity.
Okay.
But then I get these kind of quantity corrections here. So in some sense, this tends to diffuse the quasi-particle, but if I have like this attractive interaction between them, it tends to keep them closer together.
And so how do they relate to these two circle pictures?
Oh. Here, I have a hole on one side of the quasi-particle, on one side of the Fermi surface, particle on the other side.
Okay.
So
those are the attraction.
So those are exactly
Okay.
in the gauge field case. So I have some vertex. So yeah, in my early notation would be like a dashed line here. But if I have a gauge, like a vertex line between these two lines, that will be like enhanced. And if I have instead a Cooper type vertex, then this will be suppressed. In fact, there's a second thing to take into account, which is basically just a phase space argument. Namely, if I have particle scattering, so I'm scattering the Cooper channel, and this particle scatters from some point of the Fermi surface to a different point, then the opposing particle will also scatter to some point on the Fermi surface. Whereas if I'm scattering the particle hole channel, it's just again momentum conservation, this particle scatters to a point on the Fermi surface, well then the hole scatters away from it. which tells us that generally this type of diagram will be more important than this type of diagram. So if we have two mostly equivalent diagrams, the only difference being that in one, particle scattering is happening in the 2kF channel, and one is happening in the Cooper channel, we can immediately deduce that this one will have a bigger value, or will be more important than this one over here. So,
This is for pneumatic case or in general?
For the pneumatic case, it's just the other way around. Like in the gauge field case, this one is more important. No, sorry. You're right. This is always the case. Because, yeah, just a phase-space argument. It doesn't know about the sign.
Yes.
So
But for pneumatic, it's particularly true, though. Is it, or for gauge field, it's particularly true?
it's always true.
It's always true.
Right.
Because of the nesting, it's a kinematic
Exactly,
argument.
yes.
Unless Fermi surface had parallel sheets on it, or parallel lines on it.
Yes, exactly. That's why I want to say value of curvature is actually important to keep track of.
Of course. But what I'm trying to say is that, as you nicely explained with your ampere analogy, the current-current interaction for gauge fields in pneumatic case do have, in fact, opposite behavior, particle Hall versus Cooper.
Yes.
So I'm saying, doesn't pneumatic get more contribution in the Cooper channel than gauge field?
Yes, this is exactly the point. It's,
Okay, good.
as I was saying before, for the pneumatic case, the Cooper vertex tends to enhance the vertex. And also here I'm telling you that the Cooper one is generally stronger than its 2kF corresponding piece. So for the pneumatic, we expect much stronger enhancement of such kind of vertex than the 2kF case. Which in fact is perfect agreement with what we found before, namely for the pneumatic case, we did find a change in dimension of the fermion, because this guy was the more important one, whereas for the 2kF case we did not. So why does the Ampere's law allows us to decide on the sign of a single diagram? This argument actually allows us to an overall sign of two diagrams together. Right, so in going back to the self-energies, in the pneumatic case, this one is stronger and it wants to enhance the self-energy, so we get a singular piece. In the gauge field case, this guy is stronger than this one, and this one suppresses it, while this one enhances it. So we get a higher dimension.
I'm a little confused what that picture on the right means,
Which
the
one?
scattering one, the kinematics thing. I don't know one above. Yeah, what does a hole above a Fermi surface mean? Like you have a hole, the final state of the hole. Maybe somehow there's additional bands or something? Or?
You don't have it's not like everything is empty about the Fermi surface. You have a hole.
What do you mean?
It's an interaction system.
I know, everything's described.
Hole is already a hole. He's just saying that if you look at scattering in the particle Hall channel, it's going to move a hole away of the Fermi surface, from the Fermi surface, even if electron sits on it, even if a particle stays on it. Whereas in a Cooper channel, you can move around the Fermi surface, basically. As long as you have two wave vectors k and approximately k and minus k, you can rotate around the Fermi surface any which way you want.
Yes, the left diagram I understand, I just don't understand what it is. Well, I guess,
They all stay at the same energy, one right above and one right below the Fermi energy. He's just talking about kinematics of wave vectors. Isn't that the case?
Yes, that's correct.
yeah, I guess I can picture it as a, initial state is actually,
Yeah.
I don't have to talk about holes at all, I can say, on
Exactly.
the right-hand side, I had a particle actually excited in that hole, right, and it fell into,
Right.
yeah, okay, now I understand.
Just things going along. Imagine that he took Fermi surface that's two parallel sheets, parallel lines.
Right.
Then these two would just be going together along. And then he would
I
get.
understand now.
Okay, so these are, the main principles. And one physical quantity which we were interested in was the 2kF vertex. Now, for the pneumatic case, this one we know is relatively boring because the 2kF vertex gets suppressed firstly by the smearing of the particle and then again because of the repulsive interaction. So we expect that for the nematic case, in fact, the singularity is much, much weaker. But it's a bit more interesting in the gauge field case, because there these two effects are in competition, and it's not clear whether this singularity is going to survive, will be the same, will be stronger, will be weaker. So, well, we just do relatively simple calculation, it's just this vertex diagram. And we find that the exponent, this is just 1/2 from the Fermi liquid. This is the spin of the particle, which is just the tree-level scaling, as I was pointing out before. And this is the correction from Ampere's law. Notice these are both the same order, because this is first order epsilon, this is 1/n. And well, at least in our controlled expansion, we can calculate this function. And then we find that this exponent is actually smaller than in the Fermi liquid, which means that even though the quasi-particle has basically lost identity, the singularity, 2kF singularity, is actually stronger than in the Fermi liquid. Now, in this...
Can you explain it? I want to understand. So the G piece, the last piece, what you call Ampere piece, that literally comes from calculating this.
Yes, exactly.
Where's the epsilon over 4? That comes from the self-energies of the legs somehow? Or?
That's just a tree-level scaling.
It's just the Green's function,
I mean, I've absorbed the RPA scaling to be basically the starting point for my calculations.
Oh, I see.
So this is just tree-level, just pieced together.
I see.
And this is what is correction.
Okay.
But it turned out that these are the same order.
Okay.
And so combining those, we find enhancement of the singularity. Now whether it actually enhanced or stays the same or maybe slightly weakened, it's up to how much you want to trust this kind of expansion. But the point is that it seems that this singularity is definitely still there. And that's maybe a surprising point. And what has led, like Central in this talk last week, to talk about this idea of using the cone anomaly as a means of directly detecting the presence of this Fermi surface.
Should one read too much into your calculation and in fact argue that you have a line of Fermi liquids as you move along epsilon n equal to something?
Line of Fermi liquid?
So I can make that correction 0 by making n equal to g over epsilon times 4.
Yes.
So what I'm saying...
I mean, at this point, this happens to coincide with the Fermi liquid, but the scaling of the Green function, the scaling will still be different. You still have no well-defined quasi-particle. It's at like epsilon, so no, it's not a Fermi liquid. Just coincidental.
One cannot find. There is no, at the vertex level, there is no correction.
Right.
Okay. But that must mean something, though.
Why should that mean anything?
Well, it may mean some symmetry, you say. Very often, self-energy and vertex corrections cancel.
At that point, the next level is going to give it some change again.
But so if you, this obviously depends on epsilon n. So by changing epsilon n, can you change the sign of this epsilon over 4 minus g over n?
Yes.
Okay, so then no.
Sorry?
So that then when you say phi 0.4, it's just an artifact of choosing small n, large epsilon. But then a large n limit could be either larger than a half, a small phi could be either larger or smaller than a half, depending on how you take your large n limit.
It depends on what you... Yeah, I mean, sure. As I was saying, I wouldn't put too much faith in this kind of value, but it seems at least conceivable, or I think it's quite plausible that the singularity at least survives, which is, I think, the main statement in this controlled expansion at least.
Singularity meaning deviation from the square root.
Sorry?
You mean deviation from the square root?
No, I mean that it actually does remain like something close to the square root at least. You gain some similar feature. It doesn't get softened out to say a three-dimensional behavior.
But that's because it's proportional to epsilon, and it's a small correction. So yeah, I cannot deviate too much from.
No. I mean, in the end, it's an epsilon to 1.
You don't compute epsilon equal to 1.
Right, but that's in some sense it's meaningless because you don't know what happens when epsilon is 1. You can only study what happens when epsilon is small.
Sure. But that's always the thing what you do when you do large A expansion also, right?
And so that is not present. meaning that it's for sure, then of course it will be close to the half.
No. But in the extrapolation, this might well have, been a positive number, maybe even out of the 1.
In a large n, it cannot be a large number. It has to be a small number. So that's the end of it.
Yeah, but once he puts n equal to 2, but he's
but
telling
then
you.
you don't trust it. How do you know?
Well, but he's saying
there
that.
are corrections to that which are like 10 times bigger.
I agree, but I think he's trying to make a point that even at this level, when you take n equal to 2 and epsilon equal to 1, you still get 5, which is 0.4.
Yes,
I think that's his point.
Mm-hmm.
Is that fair to say?
Yeah. Yeah, well, sure. And if I take the literal limit, then these guys are suppressed. That's clear. That's again, it's as much as how you want to trust like the general large n and extrapolation from that point. I would say this is as good or bad as it generally tends to be.
But the square root, just when the question is 0, I'm calling that Fermi liquid because if I did nothing, but simply you threw away the gauge field, threw everything away, computed the Gaussian fixed point, I would get the square root? In this type of correlation function? I just don't remember the answer.
Oh yeah, just generically for a Fermi liquid into the 2k singularity of the square root.
Square root, yeah.
Right, so yeah, what does this mean for the spin liquid that we written out earlier? So firstly, at least up to this, instability down here, the properties do appear to, follow the RPA answer. So the experimental data which I presented to you last week do agree with the results from this calculation, which is essentially just confirms the result of the earlier RPA and large n calculations of this regime. Yeah, the 2kf singularity is present, I was arguing before, which raises exactly this possibility of using it to detect the spin liquid state. And basically I want to say what's the spin liquid. So this is a take-home picture I'd like to advertise. This is a diagram in the large n epsilon parameter plane. So here is the one n equals 2, dv equals 3. That's the original theory we're interested in. Then the large n approaches, they don't change the exponent, they just try to extrapolate from some large n value to this point. And here I try to convince you that this is actually problematic for various reasons. Firstly, because it's not controlled, and secondly, because there even seems to be some instability there. A different approach would be to keep n, if you keep n fixed, might as well leave it at 2, or from any point down here, and extrapolate just by expanding small epsilon to reach the fixed point, which was done by Nayak and Wilczek, which is technically challenging. And now our new approach, which is combining them to approach this point from down here, which is now a controlled limit. And, well, you can calculate singular structures. If you want to believe them or not, that's up for debate. But in principle, it's controlled, and we can do some calculation. And what we find is that the RPA is essentially correct, up for some leading corrections, or this piece in the 2kf singularity.
How did you find the shape of the curve which separates unstable?
Oh, it's an educated guess. I don't know.
But what if it's horizontally?
Sorry?
What if it's just goes straight?
This, yeah?
Right? Yeah.
That's a possibility.
That's a possibility. In our paper, we actually have this as an alternative thing. In that case, you don't know what to do. Sure. But if something can be done, then it seems better to approach it from here than just starting in the definitely unstable region to begin with. Yeah, and now that we have some at least control of this theory, this can be used to calculate various phase transitions out of this kind of state and maybe into this sort of spin-on kind of state down here. That's it. Thank you.
So when you say RPA is essentially correct,
Yes.
I just want to understand that statement. So what you mean is if had you done conventional 1/n expansion to any given order, you would be able to find some correspondence between your results for judiciously chosen epsilon times n and the results of these conventional RPA type diagrams that arise in a standard 1/n expansion. Is that what you're trying to say?
What I mean is that the same diagrams contribute to the same order as the expansion.
But they are not necessarily numerically the same because
They're
of
not
your
numerically the
procedure.
same, no.
Because of it's the same diagrams that
Yes,
contribute.
the same diagrams contribute, and for instance, in their paper they also find if they extrapolate to n equals 2 an enhancement of the 2KF singularity. So,
Thank you.
No more questions? Thank the speaker again.